Welcome, Professor Bright here, and we're going to look at now solving logarithmic equations. We just finished exponential equations, so naturally we want to talk about logarithmic equations. We really haven't worked with these too much yet, other than solving something like this first one, where if it's like log base 3 of x minus 1 is equal to 2, we said, well, okay, if we want to determine the value of x, or more generally just switch it out of log form, we can convert it to exponential form. And if we do that, we end up with x minus 1 is equal to 3 squared, also known as 9. So then if we solve this, x is equal to 10, and then usually at that point we said, oh, okay, I got an answer, I'm done. Now we'll see that this is not the case. We actually have a step after this, but it ends up working out. Okay, so we've seen stuff like that. We've also made the connection that if with that injective property that we saw with exponential functions, right? We said if we have same bases, then we just set the exponents equal. Same thing with logarithms. If you have the same base logarithms on both sides, drop them, and we can just say if we have a context like this, say x squared plus 1 is equal to 5, well, okay, then I can solve this. X squared is equal to 4, and then x is equal to plus and minus 2. Remember, if you introduce a square root, you need a plus and minus. Okay, and then we should check this and all that good stuff, and then it ends up working out. Okay, so we've seen a couple different types of equations so far. Use a definition from logarithmic to exponential and use that injective property. Okay, but now in general, how do we solve a logarithmic equation? Well, you remember we had a four-step process generally for for exponential functions. It kind of translates pretty well to logarithmic equations, but let's kind of work through an example. Okay. Most generally, I want to be able to, use the definition from logarithmic to exponential form. So to do that, though, I need the logarithmic function completely isolated. So that is to say divide both sides by 8 first in this example. Okay, so maybe step 1 is isolate. And then I end up with log base 4 of w plus 6 is equal to 3. And then after I get in this form, I want to write it in exponential form. So this is 4 to the third is equal to w plus 6. Now, this ends up being step 3 in our process. I'll talk about step 2 in a moment. But so I'm going to say convert to exponential form. And then lastly, it's just solve. So if this is 4 to the third is 64, 64 minus 6 is, 58. Okay. So, and then boom, we're done. Okay. So step 4, this is solve. Okay, and there actually is a step 5 here as well. Okay, let me fill in the blank. So isolate a logarithm. Okay, and step 2, now we are going to see equations where we have multiple logarithms. So you might want to use properties of logarithms. Okay, I'm doing shorthand here, to condense into a single log. That's why we focus so much time and energy on condensing and expanding. Okay, and step 5, this is perhaps the most important step, is to check your answer. Okay, and how we check it is we look at the logarithm that we have. So we look at log base b of whatever, and the stuff that is inside the log there, that when you substitute back in, needs to be positive, bigger than 0. Okay, but it's after you plug it all in and crank the number or crank the calculation out. It needs to be positive. Okay, so there we go. I gave you the general strategy, and okay, well, there's space down below for it too. But isolate, use properties of logs to condense, convert to exponential form, solve, and then check. So why don't you try to pause the video here, try this general strategy out. Okay, so try and use this with this next example. And here's my answer. So I isolated a log. Okay, it was actually given to me as isolated, so I did number one. That was the first, like the given. Okay, so this is number one. Then I'm going to use properties of logs to condense into a single log. So I had to end up moving the log base 7 of x over to the other side. And when I did, then I condensed it here into x times x minus 48 using properties of logs. Next, I converted it to exponential form. That was step 3. And then I worked on solving it in step 4. Now, I haven't done step 5 yet. Okay, so step 5, I'm going to take each expression and substitute it back in and make sure I don't need to do the calculation necessarily, but I need to make sure that everything inside is positive. So if I use x is equal to 49, the resulting equation ends up being 2 minus log base 7 of 49 is equal to log base 7 of 49 minus 48. Okay, now in each of these, 49 greater than 0. Great, boom, done. 49 minus 48, that's 1, that's still greater than 0, I'm good. Okay, when I go to check minus 1, what do I get? Well, okay, this is going to be 2 minus log base 7 of minus 1. And I can go further, but I can tell you this is not good because this minus 1 is negative, and that doesn't work as far as a requirement. So this means that negative 1 is an extraneous solution, so I would omit it, and I would only report x is equal to 49 as my final answer. Okay, so you can get two answers. You might get one, you might get none, you might get both of them. Okay, you need to check all of them. Just again, at the end of the day, you need to check that the answers or the values you get produce positive values inside the logarithm once you evaluate them.